In this lesson, we're looking at solving first-order differential equations in the form dy dx is equal to f of x. So basically, we're looking at scenarios where we have a differential isolated and it's equivalent to some function involving the variable x. So e to the power of x or 2x squared plus 3x. The variable will always be x in this scenario. So this is the simplest form of our ODEs in separable form. The process is pretty simple. The idea is that we can separate the differential and then perform integration on each of these separate sides. So the idea is, in this case, if we have our dy dx is equal to f of x, this dy dx can be split. So we've got our change in y and our f of x change in x. Now what this means is this is technically a 1 dy dx, and on each of these sides then we have an integral. So we've got integral of 1 dy and integral of f of x dx. So that is that we end up with y is equal to the integral of f of x, whatever that function is, with respect to x. Right, so that will allow us to find the general solution. And if we have some more specific data, it will allow us to find that specific or the particular solution. Okay, so basically, if you know your standard integrals, and most of this process is about just integrating and isolating the variable, which is, I guess, is a new step with differential equations to end up with our general solution. So we'll look at a few examples and you'll see how straightforward it is. In this first example, find the general solution of each of the following. A, we have dy dx is equal to x to the power of 4 take 3x squared plus 2. So we know this is a polynomial, and when we separate this differential, we end up with 1 dy, that's an integral, and the integral of x to the power of 4 take 3x squared plus 2 with respect to x. Integral here, integral of 1 dy will be y, and we've got x to the power of 5 on 5, 3x cubed on 3, 2x, and don't forget the c. So we end up there with y is equal to 1/5 x to the power of 5 take x cubed plus 2x plus c, and this gives us our general solution. With part B, we've got dy dt is equal to sine 2t. This is the same scenario. We can see that this dt and the variable on the other side are the same. So we end up with 1 dy and sine 2t dt when we separate the differential. And therefore we've got an integral on each side. The integral of 1 with respect to y is y. And the integral of sine is going to be negative cos we've got this 2t within, so it's negative 1/2 cos of 2t. And don't forget Charlie plus c. And again, we've got our general solution. When we look at c, we have dx dt is equal to e to the negative 3t plus 1 on t. So we've got two separate terms here. Same approach, we want to separate the differential, and now we have 1 dx is equal to e to the negative 3t plus 1 on t dt, and we end up with an integral on each side again. Integral of 1 with respect to x is x. Integral of e to the negative 3t is negative 1/3 e to the negative 3t. Integral of 1 on t is ln t. And don't forget Charlie. So we get our x isolated, and this is our general solution. Finally, when we look at D, we're looking at dx dy is equal to 1 on 1 plus y squared. Okay, so same approach. We can see the variable on this side is y. We can separate this differential, and we've got 1 dx We've got 1 on 1 plus y squared dy. Now hopefully we can see the pattern here. We can see that this is a over a squared plus y squared or x squared variable. So this becomes a tan. So we have x is equal to arctan of y on 1, which of course is just y, plus c. So x is equal to arctan of y plus c. There we have it, 4 simple differentials in this form. Again, it's just a matter of applying different integral techniques that we've already covered in Unit 3. Okay, when we look at example 2, we go a little bit further, but not far. It says find the family of curves with gradient given by e to the 2x. That is, find the general solution of the differential dy dx is equal to e to the 2x. Okay, so the general solution, we're looking at dy dx is equal to e to the 2x. So if we separate this differential, we've got 1 dy is equal to e to the 2x dx integral of, so we've got y is equal to, the integral of e to the 2x is 1/2 e to the 2x plus c. So here is our general solution. Now, what it's saying is that represents a family of curves. Remember, we can find a specific solution where c can be any real number, right? So by subbing in those values of x, we can get our family. Now, obviously, I made an error there when I said any real number. It can't be numbers that are less than 0 in this case. When we look at b, find the equation of the curve that has a gradient e to the 2x and passes through 0, 3. So all it's saying is that we're taking this general solution, and now we know that when x is equal to 0, y is equal to 3. So we can use that to find a particular or a specific solution. So 3 is equal to 1/2 e to the 2 times 0 plus c. 3 is equal to, that becomes 1/2 times 1, so 1/2 plus c. Now c will be equal to 3 subtract 1/2, which makes that 5 on 2. And so our equation then is y is equal to 1/2 e to the 2x plus 5 on 2, or we could just say that's 1/2 e to the 2x plus 5. And there it is, there's our specific or particular solution. When we move on to example 3, this kind of sits just outside the scope of the syllabus, but it's still good to look at. We're looking at a second order differential in this case. So what does that mean? That means we have to actually integrate twice in order to end up with what we want. So we know that dy dx will be equal to, when we take this dx across, the integral of 10x cubed, take 3x plus 4 with respect to x. And so if we find this integral, we get 10x to the power of 4 on 4, take 3x squared on 2 plus 4x plus c. So dy dx will simplify down to 5x to the power of 4 on 2, take 3x squared on 2 plus 4x plus c. If we want to find y, we end up with 1 dy when we separate this differential, and 5x to the power of 4 on 2, take 3x squared on 2 plus 4x plus c with respect to x. So we've got our y. This becomes 5x to the power of 5 on 10. We have 3x to the power of 3 on 6. We have 4x squared on 2, we have 6x, and then we've got to add in an extra constant, which will be d. And so we end up with y is equal to x to the power of 5 on 2, take x to the power of 3 on 2, plus 2x squared plus cx plus d. So hopefully that one makes sense. And it's the same idea when we look at the next differential. We've got dy dx is equal to the integral of cos 3x dx. So dy dx will be equal to 1/3 sine 3x plus c. And when we separate this differential, we've got 1 dy, and we've got 1/3 integral of sine 3x plus c dx. As that means we've got 1/3 integral of sine 3x will be negative 1/3 cos 3x, and we'll have cx plus d. So that means we've got now negative 1 on 9 cos 3x plus 1/3 cx plus d is our integral. So there's our general solution. Okay, so for our last example, we're going to look at finding a general solution with a second order differential. Okay, so part A is find the general solution, which is similar to what we just looked at. So we've got a second derivative, and we're looking at dy dx being equal to the integral of cos squared x dx. Now, we know that cos 2a is equal to 1 take 2 cos squared a, and therefore 2 cos squared a is equal to 1 take cos 2a. And therefore cos squared a is equal to 1/2 1 take cos 2a. So if we apply that across, we're saying that dy dx is equal to the integral of is equal to 1/2 of the integral of 1 take cos 2x with respect to x. So the integral will be 1/2 of x take 1/2 sine 2x plus c. Now when we take the next step, we know that we've got 1 dy, and that's equal to the integral of 1/2 x take 1/4 sine 2x plus c with respect to x. So we end up with y is equal to, we've got 1/2 x squared on 2, and we have 1/4 multiplied by negative 1/2 cos 2x plus cx plus d. So that means we end up with y is equal to 1/4 x squared plus 1/8 cos 2x plus cx plus d, and there is our general solution for y. Now when it asks us for part B, it says that the solution, given that dy dx is equal to 0 when x is 0, and when x is 0 that y is equal to negative 1/8. So we've got to do this step by step. We'll find c first. So we know that 0, dy dx is 0 when x is also equal to 0. So we've got 0 take 1/2 sine 0 plus c. Now we know that sine 0 was 0, so we end up with 0 is equal to 0 plus c, so c is equal to 0. And if we carry that down, we now know that y is equal to 1/4 x squared plus 1/8 cos 2x plus d, because c is 0. Now when x is 0, y is negative 1 on 8. So we've got negative 1 on 8 here. X is 0, so the first term is 0. The second is 1/8 cos 0. Then we have plus d. So we've got negative 1 on 8 is equal to positive 1 on 8 plus d. So d will be negative 2 on 8 or negative 1 on 4. So now that we've done that, we end up with y is equal to 1/4 x squared plus 1/8. Because 2x, we know that there's no cx, and instead of d, we've got negative 1 on 4. And there it is. There is our solution with those given parameters, with the gradient and the y value at specific points. Okay, so that concludes the lesson. That's really what we're looking at when we're looking at differentials in the form dy dx is equal to f of x. It's just simple integration. Now, it starts to get a little bit more complex as we change this type of function, but the idea is still if we can reorder them into integrals that we can calculate, then it will always be rather straightforward with our ODEs in this form. Right, thank you.